share with you the details about the Nobel Prize that was given on October 7 in the field of physics. And the main motivation is basically to correlate the theoretical predictions that have nearly taken 100 years till now, and realizing the theoretical predictions at a very macroscopic state, where you are not temporarily looking for quantum mechanics at the atomic state, but you are actually verifying the same quantum mechanical laws in an electrical circuit. That means you are verifying the same quantum mechanical laws at the very macroscopic scale. And as all of us know that the Nobel Prize 2025 is given to John Clarke, Michel H. Devoret, and John M. Martinis. And these three people have received the Nobel Prize in Physics this year, and they received it for discovery of the macroscopic quantum mechanical tunneling, and obviously the energy quantization in an electrical circuit. As you know that when we go with the theoretical predictions of the quantum mechanics, to be precise, when we state out our problems at very microscopic scale in terms of atoms or nuclides. So for an atom, the predictions of the quantum mechanics are like that of the quantization of energy. In an atom, you have electrons, and these electrons can only be in the states which are quantized. There are only selected states in which the electron can reside in an atom. So that is our microscopic prediction. That prediction is valid. It's valid in macroscopic systems as well, when we go into the framework of theoretical superconductivity, and we explain the formation of Cooper pairs, which was led by the three people, Bardeen, Cooper, and Schrieffer. Now that theory, what's called as BCS theory, it's a macroscopic theory predicting the quantum mechanical behavior at the macroscopic scale. Now what's happened here is that these three guys have actually they have worked independently on the same problem, and bringing the parts from their source laboratories and making an electrical circuit and confirming the quantization in electrical circuits. That means I can say at this point of time that your whole electrical circuit can be assumed as an artificial atom, because this whole electrical circuit is experimentally, it's being realized in the laboratory that it's behaving like an atom. So this is how the Nobel Prize has been given for experimentally confirming the validity of quantum mechanics at the macroscopic scale. So to start with, if I quickly summarize what I'm going to talk about, is that we have Nobel Prize in physics, and it was awarded on October 7th, I mean yesterday. It was given to Clarke, Devoret, and Martinis. And what was so important about it is recognizing the experiments that these people were performing independently, showing the quantum phenomenon in these superconducting circuits. You have an overall overall circuit, and this circuit is behaving like an atom, having all these discrete formal kind of energies. So this is what motivated, and this is what was basically the prize motivation for the development of superconducting quantum bits and quantum technologies, because they can be the basic sources to develop a full-fledged quantum computer. Talking about these Nobel laureates, we have John Clarke from University of California, Berkeley, born in 1942. Then we have Michel H. Devoret from Yale, 1953. Then we have John M. Martinis, University of California, born 1958. These are the three guys who have received this Nobel Prize for doing this great innovative job where they could experimentally, precisely confirm the quantum mechanical behavior of an overall electrical circuit conducting, involving those inductances and capacitors and maybe those Josephson junctions. So certainly the prize motivation, it was the discovery of this macroscopic quantum mechanical tunneling and the realization of quantization in an overall circuit. And what it has done, it has placed the quantum mechanics at the macroscopic scale, because till now we have been experimentally confirming all the results of the quantum mechanics at the actual atomic and molecular states. But you are able to execute a full-fledged quantum mechanics at the macroscopic level, where you have a complete electrical circuit and building, becoming a foundation for quantum computation. Now, to go with the historical background, so it's a long time. What we have when the superconductivity was discovered, it was predicted by Josephson, what we call as Josephson junctions, that you can, if you have, suppose you have two superconductors, and between the two superconductors you drag a thin insulating layer. So when you drag a thin insulating layer, it's possible for these Cooper pairs. Cooper pairs are basically the bound pair of electrons. The bound pair of electrons forms a Cooper pair. And what does Josephson junction tell us? It tells us that these bosons, these Cooper pairs, they can tunnel from one superconductor to another superconductor without taking a geometrical path. They just will tunnel from one superconductor to another superconductor. So this was the basis of this Nobel Prize, which started in 1962. And in 1980s, we had experiments, and these experiments were used in junctions, superconducting circuits, to detect these macroscopic quantum mechanical effects that could be predicted between the two superconducting materials. Now, look at this. What I'm trying to tell you about the Josephson junction is, if you see this washboard potential, if you look at this potential, you can see the hills are going on up and down, up and down, up and down. So if you think about this diagram, if you think about this in a classical sense, and you have a ball, and your ball starts, say, from the bottom of this graph. So what's going to happen is that you classically think that the ball is going to go up and then come down, and go up and then come down, and go up and come down. That's pure classical physics. But here, what is possible is that the ball may be found to cross this hill without actually going up to the hill. The ball may certainly appear on the other side of the hill. So this is what is characterized as the quantized energy levels. So what's happening here is your ball is tunneling. It's tunneling, it's disappearing from one side and appearing on the other side. It's something like teleportation. You are teleporting this ball without making this ball to go up to the hill. The ball doesn't go up to the hill, it simply tunnels, it tunnels. This is what is the prediction of the quantum mechanics. And this is what becomes the basis of teleportation, which has been experimentally realized now in a macroscopic circuit. So this is what's called as this is a washboard potential. So what we have here is this washboard potential. What we have discrete energy levels in superconducting circuits leading to the tunneling between these walls. So your ball is not actually going to the top of this hill. The ball is able to crisscross the hill and be on the other side of the hill. That's what is achieved in this experiment, in this Nobel Prize winning experiment. So what is a macroscopic quantum tunneling? So what you have quantum states. They escape from one potential well to another potential well, despite of having these classical barriers. They don't need these classical barriers to be taken on. They can bypass them, they can teleport these particles. And the next point, that this MQT shows entire degree of freedom of a circuit. And what's that degree of freedom of this? It's the phase across a Josephson junction. What they do, they behave purely quantum mechanically. So the key evidence for this experiment is the escape rate with temperature dependence and energy quantization that is observed for this particular experiment, confirming the quantization, confirming the tunneling and the quantization of energy. Now, to take a simple example here is what you have an electric circuit. Now, believe me, you have to treat this whole electrical circuit as an artificial atom, because this whole system is behaving as an atom, which is purely working on the principles of on the basic postulates of the quantum mechanics. What you have an inductance, then you have a capacitor, and then you have the Josephson junctions. And this is what is making this electrical circuit. And this whole electrical circuit is supporting the existence of quantized energy levels. That means this whole electrical circuit can be treated as an artificial atom, because it's at the macroscopic level, it's behaving like an atom, executing all the rules of the quantum mechanics. So what we have here is, we have circuits with non-linear elements like JJ, Josephson junctions. What they do, basically, they form the anharmonic potentials, the discrete energy eigenstates. So when you do the microwave spectroscopy, what it reveals discrete transitions. You don't have the continuous transitions between these states. There are discrete transitions. And these discrete transitions are we're labeling them as direct evidences of quantization. And in addition of that, so we have that theoretical starting point. We have that theoretical quantized energy eigenstate. And these eigenstates can be treated as the ket of 0 or ket of 1 as quantum states, qubit states in superconducting qubits. The key experiments that are performed in this field are spectroscopy of energy levels, as I said, in junction circuits. You have the junction circuits and measurement of these escape rates. What they show temperature independence tunneling in these macroscopic quantum mechanical tunneling. And observation of coherence. This is another important point while looking for the evidences. and controlled transition, because you must have a controlled transition. But now you are dealing with an artificial atom composing of an inductance, a capacitor, a Josephson junction, the whole thing happening at a very, very low scale of temperature. So these are the key things that you have to take into account. Now, if we think about the Josephson junctions, and if you see these, you have discrete points in this line. And what's happening? You start from predicting the quantum mechanical behavior of your macroscopic system. You start from Josephson's prediction in 1962 till now, 2025. Prize recognizing macroscopic quantum effects. The core idea starts from the BCS theory, and then Josephson, the predictions of Josephson in 1962 till now, because the theoretical prediction has been translated into an experimental evidence. Because science works only when you have a prediction, a mathematical prediction, and if you can translate that mathematical prediction in a repeatable experimental zone, then certainly you are doing a pure science, and you are doing an applied science, the science that works. So these quantum bits, what we call superconducting quantum bits, they use these Josephson junctions as I have described them, that between the two superconductors there is a thin layer of an insulator, and what you do is you tunnel these Cooper pairs from superconductor 1 to superconductor 2, and what they do basically, they build an harmonic oscillators as qubits. So your system is not behaving like a classical harmonic oscillator as we have LC circuit. If I have an inductance and I have a capacitor, you have a natural frequency where you will achieve resonance in the classical LC oscillator. But here, what you have a range of quantized energy states in your whole electrical network. So there is a range of possibilities of resonances. So this is the basis of many quantum processes as transmons, X-mon variants, and enabling quantum computing, sensors, and precise metrology. It has implications in industry and technology. It has basically laid a groundwork for commercial and research quantum processors. It has enabled improved magnetic sensing and quantum limited amplifiers. The amplifiers that will work on the quantum mechanical gates, which are basically made of these quantum amplifiers. And it certainly has bridged the fundamental physics and the practical digital technology in the framework of quantum mechanics, not in the framework of the digital technology that's working with us in terms of alone zeros and ones. Here you have infinite possibilities when you are dealing with a quantum computer. So certainly this thing has been praised as a recognition for this experimental bridging between the micro and the macro. So we were experimentally targeting the things at the atomic state where quantum mechanics completely works in these microscopic systems. But now experimentally you have taken your systems to the macroscopic system. Your macroscopic system is behaving like a quantum mechanical atom, and you are experiencing the same kind of physics for the whole system, comprising of these elements that are present in your electrical circuit that you are looking for, that you're using in building a quantum computer. It certainly will have its tremendous implications in advancing the technology in terms of quantum computers, which are under process going on and on. So this bridging has basically has made them decide a Nobel Prize, and this is highlighted by the Nobel Committee as a foundational for the modern quantum mechanics, because the experiments they have performed, they are bridging your experiments from micro to the macro quantum worlds. So you are moving from the quantum bits and you are leading to a technical path. I mean, you had the theoretical framework, now you have experimental technological framework, and you can use that technological framework to move on. And what we have, as I said, you have enharmonic energy levels, and what these enharmonic energy levels talk about the quantum states, qubits, coherence. And coherence is a very important parameter to build a quantum computer, because you want your system to remain in the same state for the longer time. Because even sneezing outside this room may disturb the quantum mechanical system. And you are performing these experiments at very, very low temperatures, and you need the shears to stop any kind of disturbance that can annihilate your macroscopic quantum mechanical systems. And then you incorporate the gate operations, and these gate operations use microwave pulses tuned to the transition frequencies. You have transitions from one energy state to another state in your quantum mechanical circuit. And the measurement techniques that are generally used is microwave spectroscopy and time domain pulse experiments. These are the measurement techniques read out via dispersive coupling to resonators, cryogenic setups, reaching to the temperatures of the order of millikelvin states to suppress the thermal activation, because you certainly need to have an environment where you are dealing with your system, with your electrical circuit, which is working quantum mechanically as a whole, which is working as an artificial atom as a whole. For this, what you are doing is you're making sure that there is no thermal disturbance to your system. So you are carrying out this experiment at very, very low temperatures. You have to have a shield that will protect your experiment from the external disturbances and suppressing any kind of thermal transmission to your system. So these are the important parameters that you have to carry when they have performed the experiments based on this electrical circuit behaving as an artificial atom. So what we have decoherence, because, as I said, a small disturbance can certainly dilute the whole electrical system, which is behaving as a whole as an artificial atom. It can disturb your system. So you want to get rid of this decoherence that may disturb your system. And for that, the research is going all around the globe, and people are working. They are manufacturing the materials that can suit more, so that such kind of disturbances can be avoided, and you can have a better environment, so that the decoherence does not take the part in your experiment. At the same time, you want to scale to the error. I mean, the error should be as small as possible. So as much as you can avoid the external disturbances, you can simulate your problem to a more realistic state, and you can work on building a quantum computer based on these artificial atoms which are behaving quantum mechanically at the macroscopic level, for which these people have received the Nobel Prize, and it certainly is going to give us a lot of engineering and and engineering reproducible junctions and control electronics, they all remain as an important part of this ongoing technological perspective based on the simple quantum mechanical laws. There are broader implications, like it demonstrates the quantum mechanics reach into the macroscopic circuits. It was not there. You are not quantum mechanically executing a mobile phone, a computer. They're all classical objects. So there is a demonstration of the new era that might be that we might have in future, where your electrical systems will have the electrical circuits working quantum mechanically and strengthening the connections between the condensed matter, quantum information, metrology, and there are further explorations of many-body and macroscopic quantum phenomena that can take on from here. So for general audience, I would like to say is that that here we are not dealing with the particles. We are not doing the quantum mechanics of an atom. We're doing the quantum mechanics of an electrical circuit. This electrical circuit can be treated as an atom, you may call it as an artificial atom. And here what you can do is you can teleport your particles from one point to another point through the barriers. If you see that washboard diagram as I showed, you can switch your particles, and they can cross these hills without actually climbing onto those hills. Then there is another important thing. You have quantization of energies available in these electrical circuits, and systems can only occupy certain energy levels. It's not going to occupy all energy levels. They can occupy only certain energy levels, like rungs, that we have rungs on the ladder. The laureates, these Nobels, have showed that these effects in electric circuits you can build and you can measure. So you can build these electric circuits and you can do the measurements on these electrical circuits. Practically what we have, we should study the Josephson junction basics, should study the superconductivity to understand in broader sense what's going on, learn microwave techniques that we use in identifying the quantization of energies, and cryogenics, make your experiment at a very, very low temperature so that there's no disturbance that can hamper the working of your electrical circuit for the experiment. And we should understand the qubits, how to design a quantum bit, like transmon basics and coherence matrices. These things are the keys to understand exactly what's going on and what these people have achieved. So the main references of this presentation is I have taken, I was just listening to the press release of Nobel Prize .org, October 7, 2027. The press release that they gave as and its popular background, and then Nobel Committee coverage, the news reports that were floating on October 7, and then selected some explanatory articles like news and physics outreach pieces to demonstrate this presentation. And if you want to further know about this Nobel Prize, you should go with Nobel Prize Science Background PDF, and you should go to the introduction to the textbooks that talk about the Josephson effect, superconductivity, and the quantum mechanical circuits. And you should also take on some of the review papers on superconducting qubits and microwave quantum optics. The point is that in a span of 100 years, because the peak of quantum mechanics was nearly in 1925s, and then we had some breakthroughs like BCS theory. Over 100 years, this this whole picture has come to a conclusion. I mean, you started with the basic laws of quantum mechanics, and then you reached out to superconductors, then you reached out to the Josephson junctions, and finally you have the people who are receiving the Nobel Prize in the same field. So now we can understand the broadening of this quantum computation and the broadening of science, the broadening of technology in the framework of quantum mechanics. So with these words, I would like to say you goodbye.